Okay, the first topic to address on the quiz, a few of you have been emailing me about the first question, which was the question that I claimed was the easy question. In particular, for the second problem, the second part of the first problem. And you've been claiming that your probability calculations on the gates are incorrect. Oh, by the way, since I'd meant to email all of you, so the two quizzes are up on the Moodle site. So you have to go to the Moodle site, you'll find the two quizzes. And the slides are up on the course wiki website. I'll maintain that schizophrenic policy when it comes to posting stuff. So the Moodle will be used for posting quizzes and grades, but not much else. And on the wiki website, slides, videos, and handouts and information. But regarding the quiz question, it was something like, I've forgotten what the exact circuit was. So something like this, where this is an AND gate, this is an AND gate, this is an OR gate. And so it seems like a trivial problem. And I give you the probabilities for A, C, B, for A, B, C. So you substitute the probabilities, you multiply them. For an OR gate, as many of you have found, I hope, for an individual OR gate, if we've got X and Y, so can someone tell me? So Yao, what is, given probabilities X and Y, how do you compute the probability for an OR gate?
There's a formula for this, but I don't remember it.
Anyone?
X plus Y minus X plus.
Yeah. And so this should look familiar to you if you recall vaguely from high school's Venn diagrams and all that. I think every high school student learns Venn diagrams. This is the union. And an OR gate, in the context of probabilistic logic, is a union gate. So an AND gate is an intersection gate, and an OR gate is a union gate. And you also remember Venn diagrams for probability theory. So, okay, so a circuit like this seems very easy. You just multiply these probabilities, and take the sum minus the product of the probabilities. Except not so quick. There's a little twist here. I'm not going to give it away. Well, but can someone point out, without giving it away, what is the twist here? C is repeated. There's a C here and a C here. Now, the intent by using the same variable name is these two C's are not independent. They're identical. So whenever you receive a 1 here, you receive a 1 here. So it means that you can't just change the variable names to probabilities and work with the probabilities as though they were independent events. This isn't hard, but that's the little twist, and it might be why some of you are taking the naive calculation, plugging it in, and not getting the right answer. I don't want to give away more than this, but are there any questions? Yeah. Okay, I think this is pretty simple. All right. For the second problem, it's simply tedious, but as I mentioned last time, for quiz 2, rather, you simply have to look up what Bernstein polynomials are and go through the calculation. Okay. What I'd like to do for today, and this will be the last lecture on the topic of computing with probabilities, and it'll also be the last lecture which has an explicit logic design emphasis. So again, to the non-computer engineering students, a bit of an apology today. I'll continue to talk about AND and OR gates. I suppose it's only when you see the homework that you can give me feedback as to whether some of this is gibberish or not. I'm not oblivious to the fact that what seems obvious to me, what seems like something that I've explained very carefully so that anybody with no background can understand, probably isn't. I say this because a couple of experiences. So I studied electrical engineering. My sister studied neurobiology. She's just a year and a half older than me. I went to her PhD defense and sat through it. Understood nothing. It's incredible how little I understood. And obviously she did a great job presenting it. And then she came to my PhD defense, and she understood nothing. And both of us felt that in our presentations we had started right from the basics so that anybody could follow it. And I realized that there's more of a gap between disciplines than most people imagine. And in general, when it comes to explaining things to an audience, and this applies to some of the smartest people, I'm not saying that's me, but people are oblivious to what the audience doesn't understand. And it's a real failing of our species, and our failing of our species and our ability to communicate technical subjects. So, okay. That was by way of apology that today, again, I'll be talking about AND and OR gates, even though some of you probably haven't seen that topic before this class. So what I'll be speaking about today is actually not AND and OR gates, but a different model of computing that I think most of you in electrical and computer engineering and computer science have seen because it's quite simple and intuitive. So often a course in computer engineering starts, or in logic design starts, with a switch-based model of computation. So without me explaining what's on the screen, can someone explain what a switch is and how a switch implements a 0-1 function? How about someone new, a new victim who hasn't spoken? Instead of me calling on someone, can someone lift up their hand? How about, I have no choice but to call you guys by your clothing. How about in the purple shirt, 4 rows up? Yes. So if I show you this diagram, which is x1 and x2 connected in this configuration, and I talk about series versus parallel, what's your understanding of that? What's your name, first of all? Liu. Yeah.
I think parallel, either x1 and x2 is closed.
Very good.
So it's a closed.
Very good.
And for the second one, it's often should be closed.
Perfect. And so in terms of the logic functions that we know, what logic function does this implement? And this one? Perfect. So this is very intuitive, and in spite of my advanced degree in electrical engineering, I actually know nothing about electricity. I'm designing a house. You guys saw the plans or the sketch of it. And the discussions with the people who are going to do the electrical work, when they see my business card that says Professor of Electrical Engineering, suddenly say, oh, and they don't realize I understand nothing about how to wire up a house. It's actually annoying. For those of you who are getting degrees, you'll see that your neighbors, for instance, when they learn that you have a bachelor's, a master's, or a PhD in electrical engineering, they'll come to you with questions about how their house is wired and what the problems are. Or even worse, they're going to refer their teenage son who has a problem with his car's stereo and ask you to fix it. And maybe some of you know how to do this, but I look at this and I have no expertise whatsoever in fixing faulty wiring in a car stereo. Anyways, so my understanding of electrical wiring basically is this, that you can have a switch, like a light switch, and when the switch is closed, there's a connection. When it's open, there's not. This is a very fundamental model. And I do this a lot, but let me digress for a second to tell you guys a bit about the history of this model. This model is often called, these are called switching circuits. And this is the model that Claude Shannon considered in his very early work. So first of all, has anybody heard of Claude Shannon in any context? Yes, Paul, right?
Yeah.
Paul.
Pioneer of
Information theory. So that's what Claude Shannon is known. And in certain circles, he's an incredibly, he died, I think, about 15 years ago. He's an incredibly famous guy. The entire field of information theory is based upon work that he published in 1949. So can you tell us just a little bit, what is information theory, Paul?
Information theory is like the study of how you efficiently communicate information, with and without loss.
Perfect, yeah.
And like what the maximum amounts of information you can communicate
Yeah.
over a given channel are.
Yeah. So this obviously would be a topic for a different course. But information theory sounds like a New Ageist type of concept that some sort of motivational speaker would talk about. But the brilliance of Claude Shannon was that he came up with a precise definition of what information is, or he labeled something that is precise information. And that's simply the mathematical content of a sequence of binary digits, zeros and ones. He made the mathematical content of it very precise. He gave a precise definition. But from that insight, he came up with a sequence of absolutely brilliant papers where, as Paul described, he fully characterized if you want to transmit information, so if you have a sender, and you have a wire, and you have a receiver, and you can send zeros and ones across that wire, how much information can you send? If you have a given rate at which you can send the zeros and ones, then at what rate can you transmit information? But he did much more than that. He introduced, that's usually called information theory as the field, but it's very closely related to a field called coding theory or error-correcting codes. He introduced the whole concept of if you're transmitting ones and zeros across a wire, it could be a wire or it could be a wireless channel, if you're transmitting ones and zeros, but there are errors that occur. So let's say there's a little bit of static. You guys are all familiar with it these days, a Wi-Fi connection that perhaps isn't good. It's not working as quickly as possible. Well, what's happening is that your iPhone is trying to talk to a base station somewhere. It could be a cell tower, it could be a Wi-Fi base station, and the transmission isn't perfect. So your iPhone talking to the base station, some of the ones and zeros that are being sent aren't being received or being flipped. So Claude Shannon fully characterized how much information you can send for any parameter that you choose of the bits not being sent properly or received properly. Now, it's hard. Okay, I'm trying to build this up without an explanation so I won't have much oomph. But it's hard to overstate how brilliant his work was in the following sense. And this is not my analysis of it. It's the analysis of an expert in the field who I heard speaking about this. That in many different disciplines, there is a breakthrough. There's a breakthrough. An example might be relativity, where Einstein came up with what many people would call the most important mathematical contribution of the 20th century. Now, a historian can look at the environment in which Einstein was working, and what he did was undeniably brilliant, but in essence, the time was absolutely ripe for him to come up with this work. There was immediate recognition for it. Famous physicists and mathematicians around the world had been grappling with the problem of the speed of light and calculations with respect to the speed of light. So when Einstein came up with the work, the world immediately, within a few years and within a few decades, he was the most famous scientist alive. Claude Shannon, when he did his work in 1949, he was so far ahead of his time. It's not that he wasn't immediately recognized for it, but it took 30 years for people to digest what he did. He was that far ahead of his time in the 1940s with this work. Essentially, he, with the sequence of papers that he published, he foresaw where digital communications would be 50 years later, where people would be really grappling with how do you send stuff over high-speed links with lots of errors. And he created by himself an entire mathematical framework. Okay. So that's the brilliance of the topic of information theory. It's a topic that I like very much, a topic that, for those of you who are interested, I'd encourage you to take courses on it. It's really an advanced topic in computer engineering, but a great one. But much less known, and in fact, it's baffling that Shannon isn't equally well known for a contribution that he made much earlier. So he made a contribution much earlier for his master's thesis at MIT in 1938, I think. So has anyone heard or read of that master's thesis? Anyone at all? Paul? So his master's thesis pertained to switching circuitry. Here was the state of the art when he was doing his work in the 1930s. There was a telephone, so computers didn't exist then. But there was a telephone grid, both in the US and in Europe and in parts of Asia. Telephones were up and running. And the way that people built the telephone grid was with electromechanical relays. So these are relays that, it's like a switch, and it's mechanical. So there's, when you apply a current to the switch, it closes, and then it forms a connection. But it's mechanical. There's a mechanical switch that opens and closes. And the entire telephone grid was built that spanned major cities in the US with these electromechanical relays. How did it work? Well, if you wanted to place a call from Minneapolis to Chicago, as part of the telephone number, and it was both automated and it was through operators. You guys may have seen pictures of the operators, making connections across the board. So operators largely would make connections, and then electromechanical switches would be opened or closed to physically route the voltage and current from your telephone receiver to somebody else's telephone receiver. So there's basically a direct connection, so that when you spoke, your voice would be transceived into an electrical signal. That electrical signal would be sent. So it was a massive endeavor to try to create a telephone system where, through mechanical relays opening and closing, you could arbitrarily connect two phones. But here's the even more amazing part. People did that. They built this telephone grid without understanding the mathematics of it. It was ad hoc. And it truly, because it's so familiar to us now as computer engineers, it's hard to imagine what the situation was. But it was basically experts who figured out by trial and error how to make connections. It was a mess. Along comes Claude Shannon, and he makes a link between electromechanical relays and a specific mathematical concept. So can anyone guess what that is? So Paul, what mathematical concept did he link it to?
What are the zeros? I don't know.
Yeah, in essence. So since the days of the Greek philosophers, but in particular the 17th, 18th, and 19th century, mathematicians developed logic. Logic was a mathematical discipline. Computers didn't exist. The mathematical discipline was reasoning about true and false. And that continues to this day. If you take a course over in the philosophy department on mathematical logic, you'll learn all about reasoning, about logical reasoning. Reasoning about something, whether something is true or false, logical connectives like and or, they call it conjunctions and disjunctions. You learn about quantification, there exists, or for all of this with respect to true or false statements. And basically the mathematicians had worked out a lot of logic, the theory behind logic. But nobody had thought to apply all of that to circuits. And Claude Shannon's, and it's hard for us to imagine that this insight was revolutionary, but he said, look, a switch being closed, we'll call that true. A switch being opened, we'll call that false. Little historical anecdote, he chose the opposite convention in his work in his paper. And I'm going to ask you guys to read his master's thesis, because it's an extremely readable master's thesis from 1938. But the one confusion is that he has all the conventions backwards. Everything is exactly backwards from what was later adopted. But he made the brilliant insight to say, look, let's call closed 1, and let's call 0 open, and then let's talk about the function in this case, a function on logical values, that describes whether or not 2 points in a circuit are connected. So here, if we look at this point and this point, we can say the function evaluates to 1, or it evaluates to true, if there's a closed path between those 2 points. So the function evaluates to 1 or 0, depending upon whether the variables evaluate to 1 or 0. Okay, but that was the opening sentence or two of his master's dissertation. But then in his master's dissertation, he went on to develop the complete theory of how you deal with such circuits. So the concept of series and parallel, that was the second paragraph. But then a full methodology, we're given an arbitrary function. How do you take that arbitrary function and design a switching circuit to implement it? And as you'll see when you read it, he writes so well and so eloquently that I would argue that it's still the best source of information on this, better than any textbook that's been written in the 70 years since on switching circuits and how they're designed. So that was a little bit of background, and I won't be talking about exactly Shannon's model, but I'll be talking about a related model that's applicable to modern day technology. So here's just an example of series parallel. just quickly, because you'll be asked to do this on the next quiz, can someone describe, and I think it's obvious to all of you, but if we have series parallel and series parallel, how would you begin to write down the function that describes whether there's a connectivity between these 2 points? So Leo, what would you do?
I think it's x1 plus x2.
Perfect. So what you're doing, I think, right away, is you're nesting the operations. So here, what Leo is saying, let's start, at the innermost nesting of it and write down, I'll use the computer engineering convention at the peril of confusing some people. So plus here will represent OR. So this represents OR. By the way, the bar above it represents the complement of a variable. So the switch, this particular switch will be closed if x2 is 1, and it'll be open if x2 is, it'll be closed if x2 is 0, and it'll be open if x2 is 1. So what Leo is explaining that we start by writing the OR of the innermost term, and then we can take the AND. Multiplication is AND. And then we can take the OR of another term. So we can nest things in series and parallel. So series and parallel, I think, you guys have all seen in high school series and parallel. And those of you who've taken courses on circuits, resistors, and so in general, linear circuits, you've learned how to manipulate series parallel circuits with resistors. And all of those techniques apply here. Shannon did much more. He considered non-series parallel circuits. Non-series parallel circuits are a lot of fun. You'll see an example in the next quiz. I shouldn't burn time on it, but Leo, can you give a quick example? What would be something that's not series parallel? A bridge. So, what does a bridge look like? So here, imagine I've got a switch, a switch, a switch, a switch, a switch. This is not series parallel. There's no way to write this particular circuit such that everything is either in series or in parallel with something else. And without saying more about it, what I'll ask you to do in the quiz is for a non-series parallel circuit, describe the function. It's easy. I think you guys will get that quickly. Okay, but that's not what I want to talk about today. I want to talk about a generalization, and I can't claim that the generalization is one that I've made, but as you'll see in a moment, my students and I have worked on the logic that applies to this generalization. So instead of a one-dimensional switch, by one-dimensional I mean a wire that connects 2 points. Suppose that we have a two-dimensional switch. So a two-dimensional switch here would be a switch in which we have actually 4 terminals, and the switch is either opened or closed, in the sense that the 4 terminals are either connected or they're disconnected. But when we make the leap to a two-dimensional switch like this, it now means that we can arrange two-dimensional switches not in lines that might be serial parallel, but in a fabric, so in a two-dimensional fabric. So has anyone, I'm always curious, there are master's students in here. Many of you are probably involved in research in areas that I don't know of. So is anyone doing work on device fabrication or nanotechnology here in the class? Anyone in Steve Kester's group? So here at the U, there's actually great research in nanotechnology. It's one of the strengths of the department. And this particular model of a two-dimensional switch is one that applies directly to many different types of modern technologies, including nanowires. So nanowires, this is a label given to different types of technologies where very, very thin wires are manufactured. And then entire circuits can be built connected by nanowires. Sometimes the nanowires are built out of carbon nanotubes. Has anyone heard of that? Anyone at all? Seamus, what's a carbon nanotube?
Just a really small wire made out of carbon.
Yeah. But it has the interesting feature, so carbon can be arranged in many different forms, obviously. But carbon, when it's in a lattice form, will form either graphite. No, it'll form a diamond. When it's in a planar sheets, it'll form graphite. But also, it can form esoteric structures like buckyballs, so a three-dimensional ball made of carbon atoms. Carbon nanotubes are also interesting and esoteric because it's a single layer of carbon atoms that naturally arrange themselves into a tube structure. And it's really one atom thick, one atom of carbon around. So it's just a structure in which carbon... Am I getting this right? Yeah? Okay. So people are really excited about carbon nanotubes because they have terrific strength properties. They have terrific electrical properties. They can have semiconducting properties. So lots of people are very interested in looking at carbon nanotubes as a next generation material, including a next generation material for circuitry, to actually use the carbon nanotubes, their semiconducting properties, to build circuits. And there are other techniques for growing nanowires. A defining feature, perhaps, of nanotechnology is that, as a label, actually this isn't a good label for the entire field, but for nanocircuitry, is that instead of focusing on techniques that explicitly arrange the circuit structure in conventional circuitry made out of silicon, so-called CMOS circuitry, the structure is made by directly patterning where the wires and the transistors go with a mask and with UV radiation. With nanotechnology, what people are looking at is techniques for self-assembly, so techniques where you could build a circuit that it doesn't grow in a biological sense, but you grow it through a chemical process. You seed the process, and then, for instance, the wire self-assembles. So you provide all the ingredients, you provide the environment, but you can get the nanowire to grow. And people have succeeded in growing such nanowires with incredibly small dimensions, literally atomic scale dimensions. And so they have these fabrics that consist of nanowires, incredibly small, incredibly dense. And they've created two-dimensional fabrics, so nanowires that cross nanowires. And that's exactly where this model comes in. So you have the potential for circuitry that has densities much greater than conventional electronics that consists of these tiny, tiny, very dense nanowires arranged into two-dimensional fabrics. So the two-dimensional switch would be a model in which you can take such a fabric, and assuming that from a layer above, you can control whether or not two nanowires are connected, or a region of nanowires are connected, then you can have switching circuitry. And so this is the model that I'd like to consider, and I'd like to talk a little bit about how we can synthesize, by synthesize, that's jargon, I mean how we can take a desired function, a target function, a design function, and implement it in a fabric of such nanowires. So here is a simplified view of how the computation will proceed. So imagine that, I think what I'm illustrating here is, first of all, that instead of drawing out these switches, which I could have if I wasn't lazy, I'm just going to use a checkerboard type of setup where for a given switch, I'm going to represent it as closed if it's a black square and as a white square if it's open. All right. Now, how could you, so here's a network of 9 switches. How could you begin to define a logical function on this? So Jack, how would you define a logical function that operates on this?
Maybe based on which sides are connected to each
Yeah,
other.
perfect. So here, what we'll do is, and this is pretty much arbitrary, we could have chosen left to right. We'll focus on top to bottom. So we'll assume that there are 2 plates, top to bottom plates. These are analogous to the source and the drain, or the 2 points in Shannon circuits. And we'll say, all right, the function that it implements is a function that's 1 if there's a connection from the top plate to the bottom plate, and 0 if there's no such connection. And the reason why I labeled the left and right is when we start talking about the design technique, I'll speak about the connectivity from left to right, even though in the examples I give, we won't be actually using the left to right connectivity. Okay, so any ideas? Let's say that why don't we take this function that's up here, and how would you implement it in a network of these switches where, assume like before, that each switch can have a particular variable pinned to it. So here we might have the variables x1, x2, x3, x4, x5, x6, x7, x8, x9. Or perhaps you could repeat the variables. But how would you implement a function such as this one in terms of connectivity between the top and bottom plates? I'll let you guys think about that for a second. I always consume too much caffeine. And I'm careful to remove the microphone before I go to the restroom. Movie in the 80s called Naked Gun. In the movie Naked Gun, the protagonist, I don't know what the setup is, but he's speaking at some sort of conference and the Queen is in the audience. And he makes the mistake that I've seen many people make at technical venues. I made the mistake myself, where you're hooked up to the microphone. You forget you're hooked up to the microphone anyways. He exits and he goes to the restroom. And it's pretty funny. But I made this mistake at the very first talk that I gave at a conference where it was a smallish conference, but it had maybe 50 people in the audience, and I got up and presented my work. And then I sat down still wearing the microphone, and I kind of sat in the back while they were trying to arrange for the next speaker to come up. And my buddy was seated next to me, and I continued to talk. And I guess I wasn't aware that the entire room was hearing what I was saying, and I was saying things about a given person and whether this researcher was in and how his research wasn't as good as our research, and it actually did some damage. So don't make that mistake. All right. So I'll talk about this a bit, and I'll try to describe what our so-called synthesis method is. But because it's a little bit beyond the purview of the course, I won't really give a proof or a justification for why it works. But I think the method itself is intriguing enough that it warrants an explanation. And the details, I'll ask you guys to go through some examples, and perhaps from there you can get a sense of it. But the setup is interesting, I think. So the setup is one in which I'll use the, should I dim the lights here? I don't understand these switches. Okay, so the setup is, we'll use the checkerboard model here. So each square represents a switch, and the variable controls the switch. So if the variable is 1, the switch is closed. If the variable is 0, the switch is open. And our objective is to implement a particular logical function, so a function of zeros and ones. So as Jack explained to us a moment ago, here the connectivity will be, the function will evaluate to 1 if there's a closed path between top and bottom. So if x1, x2, x5, and x6 are all 1, then there is a closed path. Current will flow. But if there is no closed path, then current will not flow, and the function will evaluate to 0. So The function evaluates to 1 if there exists a top-to-bottom path. Now, I'll also talk about this other function, which we'll call, so I'll call the top-to-bottom function f, and the left-to-right function, I'll call it g. And as I mentioned, f is the target. G will be used to explain what we're doing. So here, for this particular assignment of 1s and 0s to the variables x1 through x9, f evaluates to 1, and g evaluates to 0. Everybody's OK with that? OK. So let's consider a particular problem. And again, for everyone, but particularly the non-computer engineers, here this is a logical function where multiplication represents the AND operation, and addition represents the OR operation. So the way to read this is this function is the OR of the AND of x1, x2, and x3, and the AND of x1, x4. All right, so Jack, any ideas? How would you lay this out? Just even a naive way of doing it.
Well, I was thinking before it might have something to do with like rows and
Yeah,
columns.
it does.
Figuring out how
Perfect.
they're connected.
So if we're targeting top to bottom, then columns are reasonable. So ideas.
So if part of a given column is filled, and then part of the column next to it is, I don't know.
Yeah.
Can't really
But so just without overthinking it, if we have the OR of two terms, why not just have two columns, one for each term? Does that make sense? Because if either column is true, then we'll have a path. Okay? So what we could do is, well, here are two attempts. I'll let you look at these for a second. But here are the two attempts. Here in the left example, I take the first term, x1, x2, and x3. So logically, if x1 is 1, x2 is 1, x3 is 1, we'll have a column of 1 here, and we'll have top connected to bottom. Good. If we have x4 and x1 equal to 1, we have two copies of x1, then we have a 1 and a 1 and a 1. So if we have x4 and x1 being 1, then we have top to bottom connected here. And if either of these are true, then we have a connection from top to bottom, and either is the OR. OK, but what's the problem with this?
You can have x1 be true, x2 be true, and you can evaluate
Very good.
even though x3 is not.
So we have these sneak paths. So this one is fine. That's x1, x2, x3. This one is fine. That's x1, x4. But then we got a sneak path, x1, x2. The sneak path messes up our computation. And here's where only those who have taken a course in logic design can immediately see why. Oh, you can see why from the circuit. But Alex, can you see why from the expression?
x1, x2, x3 is redundant because x1 and x2 already exist.
Very good. So without, even though I teach the course, I never remember the names of these laws. But if we have A or AB, A or A and B, this is an expression that simply simplifies to A. So if A is true, the expression is true. And so for A and B to be true, A must be true, and so the AB term is redundant. So that's the simplification here. OK, so in other words, the simple idea of laying things out in columns was doomed. It'll never work. Except, let's look at this example here. So Alex, what are you seeing about that example there?
You can have 1, 2, 4, but that is still true because 1 and 4 can be true.
Yeah.
I think this one will work.
That's logical. If the professor would set it up this way. If they both didn't work, it wouldn't be interesting.
It still could be good. You could show different ways it fails.
Yeah. But there is the notion of being optimistic in life. So this one does work. So here we have the 1, 2, 3. We're agreed on that. We have the 1, 4. We're agreed on that. Then we have 1, 2, and 4. But 1, 2, and 4, by the same principle I just described, disappears because it's dominated by the x1, x4. Then we've got another sneak path. We've got the 1, 2, 3, and 4, but the 1, 2, 3, and 4 disappears because it's dominated by this one. And so the result is the function that we want. OK, are people following this? All right, so obviously it can be done for this example. When you have an example of a successful example, when you have a successful example, then most people immediately would say, well, let's figure out how to do it in general. So if I give you a general function, what do you do? I'm just trying to prod you guys. With the red hair, what's your name?
Ryan.
Ryan. Okay, got it. So any ideas?
Probably start with columns and then just flip things around until it works.
Yeah. That's what people did before Shannon came along. They just said, oh, let's wire it up. Okay, it doesn't work. Let's switch this, switch this. I don't know if any of you guys have experience with trying to get something to work. For those of you who program, when you're in a particular mindset and you start hacking away at things to get things to work, it'll work in some areas, but in some areas when it's just... So here, the reason to be pessimistic about that approach is as you scale up to just a few variables, let's say you have 10 variables, then there can be over 1,000 different ways of assigning ones and zeros to them. And it's just, but I guess that's what I would do too. But any ideas that are more precise than just laying up the columns and then trying to switch them around? Jordan?
I guess that's where the GFL function comes in.
Yeah.
For the limits, how it could branch into other columns.
Very good. So how are we going to, that's excellent. How are we going to use the G of L? It's really good.
I'm guessing just try to make that it can't, depending on your function, you can't have it branch off to one side or another. I don't quite know the exact implementation off the top of my head.
Yeah. So let me step through a little bit more, and I will give you guys an intuition to how it works. But first, I'll just state the method, and then after stating the method, we can discuss the intuition. But before even going there, does anyone know what the dual of a function is in terms of logic? This will be important. Someone know? Yeah, who's saying that? Alex. So De Morgan's rule is the relationship between and or. So the and function is the dual of the or function. But duality is actually a little bit more general than that. Does anybody know? I think I have this probably in the next slide, so maybe I should just flip forward. But if we have some function, so if we have some function, so some logical function of n 0, 1 variables. The dual of it, let's call it g, is obtained from f. Can anyone guess how? So Alex, how? Think, you had it exactly right. So think, how do you get between and or? Very good. And flip, so you flip all the variables and flip the function. That's the definition of the dual. So the dual of g is going to be, we take the function f, so however it's written, and we flip all the variables. And then we flip the entire function. So if we have a function f is equal to x1 or x2, x3, so this is the function x2 and x3 or x1, then the dual of it, the function g, will be if we take x1, we complement it, we complement x2, we complement x3, and then we complement the whole thing. And this, if you've taken some logic design, what does this simplify to, Alex?
X1 and quantity.
So it's the dual function. We replace everywhere we see an and operation, we replace everywhere we see an or operation, we replace it with an and. Everywhere we see an and, there's an or. For the non-computer engineers, don't worry about this step. So this function can be simplified to this function. That's part of what we teach the undergrads. It's called De Morgan's law. All right. So that's the dual here. So Jordan, any ideas percolating? How's the dual going to help us in terms of what we want?
I guess a wild guess is that you have your f function be defined as your top to bottom
Yeah.
function, and then the g of L would be the dual.
Yeah. Why? I can see some people are either thinking or they're daydreaming. So Mackenzie, you're hard at that. I shouldn't interrupt you. Is it coming together?
Just I guess a wild guess is for every condition of f that would be true, the dual of it would be
False.
false, so it can't branch off to the side.
Yeah. So the intuition, it isn't quite this simple, but what we want to do is we want to avoid sneak paths, the side-to-side paths. And so if we think of the function that's defined as connectivity between top to bottom, we want, when that function evaluates to 1, we want the function that goes left to right, if we flip all the variables, flip all the 1s to 0s, to evaluate to 0, because we don't want there to be a sneak path from left to right. Let me show you examples and explain it a bit more. The intuition is not that simple, but that's the basic intuition. So here's a more complicated example. More complicated, not really, but it just has more variables. And this is just to illustrate to you, this would be the slide where we're pessimistic. But here, if we try to lay out x1, x2, and x3 corresponding to the first term, x1, x4 corresponding to the second, x1, x5 corresponding to the third, we've laid out the columns. But now it seems hopeless because we're going to have so many different sneak paths to contend with. We're going to have these paths, that's fine. Sorry. I did. And did I jump through a lot of them? Yeah. So these paths, and then we're going to have all these sneak paths. And by the way, here's an interesting and somewhat embarrassing admission. Even though I've taught this for a while, and even though I've asked students this problem before, it's much, much harder than the problem is much harder than it seems. So I don't know, given a general, let's call this a lattice. You can call it a matrix. You can call it a lattice. Given, let's say, an n by m lattice, I don't know how to calculate the number of such paths. It seems simple, doesn't it? But imagine that instead of 9, you had 1024 by 1024, or not even a big number. It's not the size of the number that matters. But there obviously should be a formula as a function of n by m for the number of paths. It's surprisingly difficult to calculate. So if anybody would like to work on that as a research problem, I'd enjoy working with you guys. So just a note on that before you start working. So what are some obvious paths? By the number of paths, I mean the number of non-trivial paths. So this path is a useless path. We don't have to count that one. Why? Your name is John.
I have just a question
Yeah, please.
about the topic you just introduced.
Yeah.
Aren't there many known graph algorithms to find all the paths?
There are. And so this is why it's in a bit of an embarrassing admission. But none of them fit this problem exactly. This is a problem in combinatorics. Combinatorics is the branch of mathematics that deals with counting. And here, it's a question of counting the number of paths. And I'm sure the result is known in some form or some other. And I'm sure it's because I haven't tried hard enough. So if you're interested in this, give it a try. So as a start, perhaps in 10 minutes, you can write a program that computes all the paths. Maybe more than 10 minutes. But you could write a program that you're pretty confident computes all the paths. And then you can just look as, for different values of n and m, how the numbers progress. But then fitting that to a formula is something I haven't been able to do. And so, but just, so a couple of notes before you begin tackling this problem. Why is this path a path that you don't even have to consider? John, or anyone? Yeah, so it dominates, meaning that if x5, x1 is 1, it doesn't matter that you traveled here. So basically, you don't have to consider the paths that are adjacent to top. Also, what you don't have to do is you don't have to consider paths that touch themselves. So you don't have to consider a path like this one for the same reason, because if the path touches itself, it basically shorts itself out, and the shorter path covers it. This may remind you guys, probably not. In the 80s, in the 80s, when I was a child, we used to play video games in arcades, and we used to spend quarters, and a quarter was worth more then. I probably spent a lot of money then relative to what I had on quarters in arcade games. But one stupid game was called Nibbler. It's this game where you have a snake. And as you guys also know it, I think is it on YouTube? Where if you're waiting for a video to load and you press an arrow key, you can actually play Nibbler. Is it YouTube or Netflix? YouTube. So anyways, for this game, you have a snake that's going around. You direct it with the arrow keys. And the name of the game is whenever the snake eats... Yeah? Okay, but so let me finish my description of Nibbler. So you guys know the snake, whenever it eats, I don't know what a snake eats, whenever it eats a mouse, it gets longer, and it keeps getting longer, and you have to keep it moving and keep it eating mice, but it can never touch the boundary, and it can never touch itself. And so here, this is kind of like the game of Nibbler, because in terms of the number of paths that you have to count, it's first of all a path, you can exclude the path that touches top or bottom in more than one place, and the path should never touch itself. It should always go from top to bottom without touching itself. I'd just be interested if somebody could work this out as a solution to it. I haven't really tried it myself, but I tried it, for a few hours and just couldn't really make headway on it. All right, and it's a bit of an embarrassing admission because the work that I'm describing here, we wrote it up, we published it first in conference proceedings, then in good journals. And it really would have been helpful in those journal articles to have the formula. And kind of we scratched our head for a while, the student and I, and then kind of said, all right, we don't know how to do this. And we skirted around it and how we wrote it. But because the name of the game of the journal article was how to synthesize functions implemented with these two-dimensional switches. And we wanted to minimize the number of switches. And so it would have been really useful to describe, what is the space of possibilities in terms of the number of such paths that we've avoided. Okay. But there are many such sneak paths in this problem. So here is the strategy for avoiding it, and it's going to be based upon the concept of duality. So duality, this is the concept that I just described. And again, for the non-computer engineers, I hope that this is okay, because I'm using variables, the complements of variables, I'm using the jargon of our field. Just let me know if it's not making sense. All right, here's going to be the synthesis method. So let's consider the same target function, x1, x2, x3, x1, x4, x1, x5. I'll describe the method before, yes, yeah, go ahead.
I think in order to start from the top and to the bottom, you have to pass different layers. And in this function, in this expression, I think we can factor out just x1. So the first layer should be called as
x1. So that's a good suggestion. You're saying the first layer is x1. No, it's not, but it's an interesting, I'm not saying it's incorrect. That's not how we do it, but it's interesting.
If it takes the x1 as a common layer and put this on the top of the lattice, and the second layer should be x2, x4, and x5 because they cannot connect to each other. You cannot have a snake on the second layer. You can have the turning point.
Actually, I'm not sure that this is, well, let me just look at the final solution and see if it looks like what you're saying. It kind of does, doesn't it? x2, x4, and x5. This is the final solution. I'll explain in a moment. And so what comes next? Yeah?
Because this is a minimum expression, right? This expression is a minimum expression.
So that's actually a good observation, that what we're starting with here is an expression that in terms of and and or is the so-called two-level form. It is a minimal expression, yeah.
Yeah, and we factor out the x1. This is the top layer.
Mm-hmm.
Yeah, in order to go through all the layers and get the final result, we always want to pass the x1. So we put x1 on the top layer. And for the second layer, in every term in this expression, they don't have any common factor at all.
After you factored out x1, yeah.
So every element in the second layer should be different.
Mm-hmm.
Because the
Uh-huh.
And go to the third layer, I think it do the same thing.
Yeah. That all sounds good.
Yeah.
But I think it's a little bit too simple. And the only reason I think this is because the method that I'll explain in a moment is more complicated.
Simple because we got this solution from the standard SOP.
Uh-huh. But suppose that we couldn't factor out x1. So suppose that I gave you an expression that didn't have any single variable that can be factored from all the terms.
Yeah.
Then what would you do?
We just suppose the first layer is just x1, and the second layer is the x2. We just first put the necessary element into the lattice, and then we put maybe we have another consideration to put the empty as well.
Yeah. Interesting. I can't follow everything you're saying in real time, but think about it. Let's talk about it. Yeah. But before I tell you my solution, does anybody else, let me erase this. Does anybody else have ideas? Anyone else? What are your names? Rohan? Yeah.
Yeah, so what I see is, whenever I see the solution is that whenever you have rows of like less, so there's three sort of variables in the first expression,
Yeah.
2 in the second, is that the variables that are common between the expressions are like adjacent to each other.
Uh-huh.
So you see that x1 is the same in
Yeah.
the first and the second.
Yeah.
So therefore, in those two columns, they're adjacent to one another.
I think that's very close to what Yao was saying, but somehow it's different from what I'll explain in a moment, but interesting. So, irrespective of what I present, think about that. Ideas behind what's your name?
My name is Shubham.
Chopin?
Yeah, that's correct.
Yeah.
But this is not too much of a solution. I actually have a question.
Yeah.
So I am trying to get a path that connects top to bottom.
Yeah.
And we're trying to avoid the lateral paths. So why don't we just space out the columns?
That's a very good suggestion. That's a very, very good suggestion. Why don't we just introduce buffer columns of all zeros? That would work. So what we can do is just have each column be a term from top to bottom, introduce zeros or broken switches. And we could do that, but as computer engineers, we try to do better than that solution. So the idea here is to implement a function with the fewest number of switches as possible, or the area. And that would obviously increase the area. But it's a very good suggestion. Did everybody see that? And I perhaps should have pointed that out at the outset, that that's kind of the obvious solution. And we're trying to do better here. But thanks for that. And in fact, that's exactly the solution that all the practical people who work on nanotechnologies have adopted. But we're trying to do better. We're trying to use math to come up with something more clever. Why? Because that's fun. So here, let me describe my method, because there's actually, I want to describe another topic today, without really justifying it. So here's the method. We're going to start with the function. And the function is in, we'll assume that it's in a form of the OR of ANDed operations. So we'll assume that the function is given like this, no parentheses. It's just going to be the OR of AND terms. That's a particular form called a sum of products form, because it's going to be the sum of product terms. So we start with that as our function. Then we obtain the dual of the function. So obtaining the dual of the function is as simple as I described there. What we do is we complement all the variables and complement the function. But if we have it in this particular form, we can directly apply what Alex suggested, which was just the so-called De Morgan's law. So the dual is very simple to calculate if your function is given in this form. You just replace every AND operation with an OR operation, and every OR operation with an AND operation. Does everyone see that? So x1 and x2 and x3 becomes x1 or x2 or x3. And so the dual is that simple to compute. Just compute the dual. So now we have the function, and we have its dual, f and fd. The t here is because I'm talking about the target function. Ignore the subscript t. So we have the function and its dual. Given the function and its dual, here's what we're going to do. We're going to assign each term in the function to a column. By assign, I mean we're just going to write the term above the column. So x1, x2, x3, we write it above this column, x1, x4 above that column, x1, x5 above that column. That's what I mean by assign it. And then we're going to assign each product of the dual to a given row. So implicit in what I've done here is I took the dual function and I multiplied it all out to get it back into a sum of products form. Am I losing some of you guys? So what we have here is two functions, the function and its dual, both in sum of products form, where I label the columns with the terms from the function, and I label the rows with the terms for the dual. Just the labeling. Okay, now, can anyone guess what I do? So Alex, what do I do?
Well, I read the slide before you backed off from it, so you find what the intersection is
Yeah.
between any of the point, you put that variable in there.
Yeah. So, yeah.
Is there always only one?
No. That's the point that we discuss on a subsequent slide. Now, but it turns out, okay, so let me explain first what we do in terms of the procedure. So what we do is, by taking the intersection, I mean, here now, I just have a collection of variables, a set of variables corresponding to each term. By the intersection, I mean, we take a common variable. So x1 is common to this row label and this column label. So in the cell, we put x1. So we just do that. Here are the sets, and this is what we take as our assignment to the lattice. And my claim is that this particular solution implements the function, and it implements the function with no sneak paths. So why are there no sneak paths? Is it clear to everybody? But to answer your question, Alex. So the next example will show that if the intersection is not unique, let's say there's a few variables, you can arbitrarily pick one, it doesn't matter. So just pick one, it doesn't matter which. But why does this work? So Rohan, why does this work?
Well, I guess top to bottom is true.
Yeah.
And your right to left are based on the dual function.
Yeah.
So that means that the dual function is going to false if the real function is true.
Yeah, very good. But why? Is it obvious to you?
I'm not an electrical engineer. So
Yeah. Well, I think you're
there's some logical axiom or theorem that
yeah, but I think it's,
proves that
I think, and I have a slide on it. Where does that slide come? I'm running out of time here. I think it came. So here is a slide that illustrates why the function and its dual have this property. It doesn't illustrate, this is not a complete explanation for the synthesis method. And I want to leave the explanation aside. But just in terms of the intuition of the function and its dual, and why it's useful to consider top to bottom and left to right in terms of the functions and its dual. Here, consider the function. If it evaluates to 1 from top to bottom, that means that there's a closed path of 1s somewhere, by definition, if it evaluates to 1. The dual function is a function that we obtain by flipping all the variables and flipping the function. So if we flip all the variables here, sorry, I should give equal time to people who sit on the left or the right. Or even better, I should learn to use a laser pointer. I just like walking around. So here, if we flip all the variables, it means that for a particular assignment, we flip all the 1s and 0s. That's what I've done here. And if we had a path of 1s that connected top to bottom over there, it means we'll have a path of 0s that connects top to bottom over here. A path of 0s between top and bottom over here is a path that must block every path from left to right. There's no way you can get from left to right without crossing this barrier of 0s. So it means the left to right function must evaluate to 0. That's the definition of the dual. Flip all the variables, flip the function. Here, function evaluates to 1 because there's a path of 1s. Flip all the variables, now there's a path of 0s, and the function is 0. F is 1 means G is 0. That's the intuition of why we're going to lay out the function from top to bottom, and we're going to lay out the dual from left to right. The issue of why we can do that by simply assigning variables from the intersection set, that's a little bit tedious to explain. But I hope this intuition is resonating a little bit. Okay. Yes, Jason.
So if you had, say, a 5x5?
Yeah.
Will that still hold true when you have room to go back up and come back down?
Explain. That's interesting. So would you still have room to go up and down? So to make...
If you have 5x5, you
Yeah.
can have sneak paths that kind of come up over and back down.
You can. So they can never touch the plates, like you said. But certainly you can have a path that goes like this. But it still means that if you have ones here for the path, and we change all of these to zeros, there's no way to get from here to here. Right? The zeros, if we changed all these ones to zeros, will always block any path from here to here. Yes, John. Yeah.
From my understanding, we're relying on the assumption that the dual is true when the function's false. And
Correct.
likewise.
Yeah.
But x1 plus x2, x3, and x1 and x2 or x3 are not exactly opposite in regards to...
Yeah, did I mess this up?
So I think in this case, f can be true, or whenever f is true, the dual will either be false or true, so it doesn't matter. But if you were to start with G and go to f, then there is a situation where G is false and f is true. Because since the dual should be reversible, right?
Yeah.
So if x1 was 0, x2 was 1, and x3 was 1,
Mm-hmm.
then G would be false and f would be true. So in that case, you'd have a path going across, but not up and down.
Yeah, but I'm still confused.
So maybe. Okay, yeah, I think I see it. Yeah.
Because we definitely obtained the function by flipping all the variables and flipping the function. Yes?
You can look for a function that evaluates to false when the original function is true.
Yeah.
I guess all you need to do is to just complement the function.
Yeah.
So you don't need to actually flip the variables. Keep the variables same, just complement the function.
Right.
So that's what will give you a false when the function is true. And vice versa.
True.
If x1 and x3 are true,
Yeah.
G and f are true.
Yeah, I know. That's what's puzzling me. Yeah. My dad gave me some advice. When you get stuck like this, I don't think what I'm presenting is wrong, but I don't know how to do this. There's a limit to how long, especially when you're running out of time, you should dick around in front of the audience. So let me think about that and get a redaction next week. All right. Much to my surprise, I was told by students that they actually appreciate it when the professor lets out class early. And that's profoundly unintuitive to me because I feel like you guys paid for a ticket for a performance, and it's like the concert ending early. It's a jip, but you guys don't. So I wanted to talk about percolation, and I wanted actually to cover one more topic here. Because I have to do a redaction anyways, let's stop here 4 minutes early, and let me pick that up on Wednesday.
It should say correction instead of redaction.
Why?
Because a redaction is like pulling something back, saying it's not true.
Oh,
But you're
yeah.
not putting something up right now. You're not putting the expiration.
Correct.
So maybe an amendment.
All starting to sound like legal terms.
Maybe it should be. Keep saying that people are. That's not true.
I don't think the argument.
But it's like in his section. So why is my I saw that as a minor. When was that?
Really sucked.